Lorentz transformations, what they do is, so Lorentz transforms convert event information from one reference frame to another. And so the reference, we're going to sort of do it this way. We're going to say that there's a reference frame O, and there's another reference frame called O prime. And in particular, we're going to start by talking about what's referred to as, well, what maybe it's only me who says this, but these are event transformations. So Lorentz event transforms convert event information from one reference frame to another. So we'll say that observation frame O might see an event whose space-time coordinate could be t, x, y, and z. And what the Lorentz event transform does is it will take this event information and give us a prediction for what O prime will assign as space-time coordinates for the very same event. So the idea is one event observed by two different frames of reference, right? So it is one event. Okay, so Lorentz event transforms, that's something I'm going to show you in this video, but also there are Lorentz velocity transforms. So O will measure components of a velocity vector. They'll measure the x component, the y component, and the z component. And O prime will measure, so let's say O watches a car drive past or a rocket ship traveling through space. O prime watches the very same rocket ship and does not, in general, measure exactly the same speeds in the various directions. And so Lorentz velocity transforms are going to tell us about the connection between what one observer will assign as a velocity and what a different observer will assign as a velocity to the very same object moving through space. Okay, so that's our goal. So let me, I'm going to move on to a new piece of paper, and so let's talk about Lorentz event transforms. So we have to have first an agreement. And the agreement is about the relationship between frames O and O prime. So the relationship is our agreement needs to deal with direction, and it also needs to deal with a time synchronization. So for direction, what we'll do is O and O prime actually share the same directions. So what that would look like is, for example, here is the frame O, and here is the frame O prime. And if this axis here is the x-axis of O, this axis here is the x prime axis of O prime. And not only that, but it is the positive x prime, and this is the positive x-axis. So those are lined up. They are the same directions. If this here is the positive y prime axis of the O prime frame, then this is the positive y axis of the O frame. So the same directions. Likewise, the z-axis points up out of the page. So that's, the z prime, and this is the z-axis of O. So that they are parallel. So the positive x-axes are parallel, the negative x-axes are parallel, the negative y and the y prime axes are parallel, etc. So even though this frame and this frame will have relative motion, because that's what relativity is about, even though they have relative motion, because neither of them is rotating relative to each other, then if we have an alignment of the directions at any time, then they stay aligned, right? Okay, so that's a directional issue, but it's not just this. The relative motion, you can, so the relative motion between O and O prime is in their common x prime, and actually positive x prime directions. And we have to be a little bit more specific. O prime moves say, in the positive x direction in O. Also, equivalently, O moves in negative x prime direction in O prime. I hope you can see that that's an equivalent statement. But we have a couple of directional agreements. O and O prime, they just simply share their directions. Of course, they didn't have to, but it turns out it's just, it's easier to start this way. It's simpler. The Lorenz event transforms are simpler. Also, the relative motion is such that the O prime frame is moving towards the right relative to O. Or you might say that the O frame is moving towards the left relative to O prime. And by right and left, I mean O prime moves in the positive x direction at speed u, or O moves in the negative x prime direction at speed u relative to O prime. Okay, so that's very, I'm being very, very specific, right? Yes, so time synchronization is somewhat subtle. The idea is when the O and O prime origins coincide, O and O prime set their clocks to read 0. So what we do is we say the clocks that sit at the origin, so you might imagine there are little clocks sitting here. As soon as, it's hard to do this in front, so if this is O prime and this is O, as soon as O prime exactly overlaps so that their origins are right on top of each other, the clock in O prime that sits at the origin and the clock in O that sits at the origin, they set their timers to 0, and then they push start, right? And so after that, all of O prime's clocks, they have to, they have to sort of like organize all the clocks in the O prime frame. Remember, O prime's got an infinite number of clocks located at every location in O prime's frame of reference, and O has an infinite number of clocks sort of ambiently throughout O's frame of reference. And then they'll have to work out separately in their frames of reference how to synchronize all their clocks together, right? But this is the time synchronization between O and O prime, which are two separate frames of reference. Okay, so a lot of specific agreements, very specific, very careful, specific agreements. Okay, so without further ado, here are the Lorentz event transforms. So if an event E in, or as recorded by observation frame O, is given the space and time coordinates t, x, y, and z, then t prime equals, so t prime equals that gamma factor of the relative speed u times the quantity t minus u over c squared times x. Actually, so there's no way, if I use this a bunch, doing some problems or something and trying to remember how things go, I'll remember it. The truth is I don't remember it, so I'm actually looking at a piece of notes off to the side. So I've written t prime here. This is the gamma factor that's a function of the relative speed of the frames of reference O and O prime. Here is that relative speed again. It sits here by itself, multiplying the x coordinate in the event as measured by O, divided by c squared, speed of light squared. And it is being subtracted from, this minus sign is important, it's subtracted from the time value, the part of the coordinate of the event E as measured by O, recorded by O. So x prime has a similar looking relationship, gamma of u, and then x minus u times t, and then y prime equals y, and z prime equals to z. These are kind of simple and interesting. The point here is we were careful to organize that all the directions are the same. Since the relative motion is in the common x direction, then the transform is only really going to make a big change in the x direction, right? And so the x direction transformation from O to O prime is, it's got a mixture of space and time in O to understand how x prime will get measured by O prime. T prime is a similar issue. It's sort of related to the fact that there is, well, not sort of, it's fundamentally related to the fact that there is some time dilation and interesting things that happen to time for relative observers, O and O prime. Okay, so just a real quick reminder that gamma of u is equal to 1 over the square root of 1 minus u squared over c squared, like this. So there's the gamma of u. Some qualities to remember is gamma is always bigger than or equal to 1. It does not take negative values. Okay. So yeah, okay. Let me move this out of the way. So this is the event transformations between O and O prime. So on the same page, I'm going to put the Lorentz velocity, transforms. And these were the Lorentz event transforms. Okay, so here's the idea. Just a quick re-reference of O prime, and here is a rocket ship. So this rocket ship will be measured by O prime to have a velocity v prime, which is a vector, equal to vx prime, vy prime, vz prime, like this, right? We'll say that this is the x component of the velocity as measured by the O prime frame, the y component as measured by O prime, z component as measured by O prime. But the very same rocket ship can be observed by O, and O will assign a different set of values in general, vx, vy, and vz, right? So there's the primed information, that would be measured by O prime, and the unprimed information, that's measured by O. And yeah, so the Lorentz velocity transforms are going to connect these 6 pieces of data. The relative motion of the frames is that O prime moves in the positive x direction in O, right? So this is the relative, right, the agreement, or the specific agreement about the relationship between these inertial frames of reference. Okay, again, I'm going to look off to the side and remember some data, some stuff. Yeah, just so you don't get the wrong idea. I don't commit very many of these things to memory. I have to think about them again and look through books just like everybody else. So I'm going to transcribe this stuff over and act like, right, I remember stuff, but you know. So, so it turns out that the relationship is, so the x direction component of the velocity that O prime will measure for the rocket ship is related to the x component of the velocity as measured by O, but then there is a subtraction of u. This minus sign is because of O prime's motion towards the right inside of O, but then it's divided by 1 minus vx times u divided by c squared. And you can see that this kind of looks like a gamma factor, but it's not. It's got this mixture of some speeds. One is the relative frame motion, and the other is the speed as measured by O. So everything in here is stuff measured by O, and this mixture of that stuff measured by O can give you a prediction for what O prime will measure as the x component of the velocity. Okay, and then vy prime is, it looks like the following. So it's strange. Let me just write it out. So it's vy, but then gamma of u inverse, so it's raised to the -1 power, and then divided by the very same denominator. So 1 minus, and notice that I'm writing vx times u over c squared. So this is about the y direction, but it's got x direction information in it, as well as y direction information. And then vz actually is just the same as y, except for you switch y and z. So it's vz times that gamma factor, but raised to the minus 1 power, divided by 1 minus, again, vx, it's not vz, but vx down here, times u over c squared. And these are the velocity transforms. So what's strange is to wonder why vy prime is not just straight equal to vy. The relative motion between O and O prime is in the x direction. So why would the velocities transverse to the x direction get affected in this really strange way? And the answer is because time is also something relative, right? Because velocity is a rate of change, O prime's clocks, they run differently than O's clocks. And so that means that even though O prime would see transverse distances not change, transverse or the associated time to describe velocities do change. And so that's why the x direction velocity is showing up in here, because it's about the relative x stuff, as well as a factor of gamma, this gamma. So since it's raised to the minus 1 power, right, gamma of u raised to the minus 1 power is just simply the square root is on top instead, 1 minus u squared over c squared. You notice there are no v's in here. It's all about the relative frame motion u. Okay. Yeah, so these are important, these three things. And you can probably just remember that the y and the z directions for the events, they transcribe straight over. The transformation is the simplest it can be. You can be naive in the transverse directions, but you can't be naive about time or space in the x direction. Okay, so to sort of wrap up this video, I'm going to talk about a really interesting thing, an example of thinking with, in particular, it's the Lorentz event transformations, right? So it's an example of thinking with the Lorentz event transforms. So, and it goes underneath the subject, so you might say that this is a description of the relativity of simultaneity. So it turns out that it's spelled this way, I think. It's the relativity of simultaneity. Events simultaneous in O are not simultaneous in O prime. Okay, so in this case, we must think about two different events. Okay, and I'm going to write that they are simultaneous in O, and I'm going to put that they are separated by a distance. And this is kind of a weird distance. I'm going to say d equals to the speed of light times 1 second. So, you know, this is 3 times 10 to the 8th meters per second times a second. This is 3 times 10 to the 8th meters. It's a huge distance. The idea is, you know, since the speed of light is so fast, in any sort of human kind of, you know, amount of time associated with us thinking and making decisions, which is about 1 second. You make decisions, much quicker than a minute and much slower than a nanosecond. But here's a human scale time. But problem is we have speed of light, or these kinds of interesting long distances. I don't know. It's just an interesting distance to pick. You don't have to pick that. You can pick any distance and just call it d. So let's say that event number 1 is equal to 0, 0, 0, 0, 0, right? So these are the time and then space coordinates of a particular event, right? That's event number 1. And here is event number 2. It's equal to, it happens simultaneous, so it's going to have the same time, but it's got a different place that it happens. I'm going to say that it happens 3 times 10 to the 8th meters away. So I'm just going to shorthand that as c times 1 second, right? But I'm going to make it boring in the transverse direction. So in the y and the z, also this other event, right? 2 different events, event number 1, event number 2. They have different space-time coordinates. Okay, so they are simultaneous in O because their time coordinates are the same. But in O prime, right? So let's translate. So event number 1, we're not going to put a prime on it because event number 1 is event number 1 in either O or O prime, right? It could have called it event A and event B or whatever, event I and event J, doesn't matter. But anyway, so event number 1 in O prime. So I'm going to bring over my little crib sheet, put it right here, and we can just fill in information. So T prime is equal to, so I've got the gamma of u, right? So O and O prime have relative speed u. O prime moves in the positive x direction inside of O at speed u. So I've got the value of t. So event number 1, the value of t is 0. So I put 0 in for event number 1's t value. And then I subtract off minus u over c squared times event number 1's x location. And the x location of event 1 is also 0. And so no matter what gamma of u is, 0 minus 0 times it is 0. So t prime, right, O prime will also assign value t equals to 0, or t prime equals to 0 for event 1. Let's check out x prime. So x prime equals gamma of u, and then 0 minus u times 0. Also equals to 0. And then y prime, and actually maybe I should be kind of careful. So I'm going to go back and say that this is t1, x1, y1, z1. This is t2, x2, y2, z2, like this. So now I've labeled the event coordinate values. And over here, this is t1 prime, x1 prime, y1 prime is just the same value as y1, and z1 prime is the same value as z1, right? And I've finished thinking about event number 1. So, interesting thing is that I get the same time coordinate, and I'm talking about relativity of simultaneity, and event number 1, as measured in O prime assigns it this very same value, 0, right? Actually, we shouldn't be surprised, because this event happens at O's origin, and O has set its clock to be 0. And that was actually in our special specific agreement that we were going to, when the origins coincide, O and O prime will make their origin clocks read 0. So their origin clocks read 0. This is just because this is the setup. But the other one, event number 2, does not happen at the origin, right? So event 2 is more interesting. In O prime, let's study event number 2. So T2 prime is equal to, so let me put this, probably okay to put it here. So here's T prime. So T2 prime is gamma of U. Relative speed is independent of which event we're talking about. Right, so it's not U sub 2 or anything like that. And then, so it goes T2 minus UX2 over C squared, right? So this is gamma of U, and then T2, here's T2, it's a 0, and then minus U over C squared, and then X2. X2 is not 0, so X2 is C times 1 second. C times 1 second. You close the brackets. So if you care, you can take out your calculator, and if I give you that, you know, U is some fraction of the speed of light, you can calculate this out. But I don't necessarily want to like calculate things. I just want to think, right? I want to think with the Lorenz event transforms. So let me think about this. So there's this like minus sign. So I'm going to subtract a bunch of positive, you know, things multiplying and dividing with each other from 0. So the thing in the parentheses here is negative, and gamma of U, you'll remember that gamma of U is only ever bigger than or equal to 1. Because U is not 0, gamma is strictly bigger than 1. And so this says that T prime for event number 2 is actually negative, right? It's negative. So that means, right, straight away, we can make a conclusion. So we can conclude that event 2 happens before event 1 according to O prime. Right? That's a conclusion that we could get to without even using our calculator. All right. So, yeah, this is quite strange. So, simultaneous in O, definitely not simultaneous. Simultaneous in O prime, right? So not simultaneous in O prime. This is the relativity of simultaneity. You could go on and you could study x2 prime, you know, blah, blah, blah. y2 prime, that's pretty easy. You already know how y2 prime is going to play out. And z2 prime, etc. And they're interesting in their own rights. But we just explored simultaneity. Right. So I want to point out something associated with this example. So note, this relativity of simultaneity, is not a point of view issue. So it's interesting. You might say that here is a person, right? And they are, for example, moving. I'm going to call this person P prime for obvious reasons. And they're moving towards the right at speed u relative to another person, and this person is called P without a prime. So this person's moving, and here are two events, event 1 and event 2, and they go off at the same time. Let's say that they are fireworks. So a light signal travels from event 1 at the speed of light and gets to person P prime's eyeballs. But at the very same moment, right, these explosions happen at the same moment, here comes, at the speed of light, light from event 2. But light from event 1 gets to this person faster than light from event 2, and according to this person who's moving towards the right, with speed u relative to person P, this event happens first because it is closer. So E1 is closer to both P and P prime. So E1 will appear to happen first. Right? But that's actually true for both of these observers. The thing about these two observers, though, is they're really, really smart. P is associated with an observer frame O, and P prime is associated with an observer frame O prime. And they have infinite number of detectors and clocks. And the idea is, even after you make P primes, all of P prime or O prime's detectors everywhere, and all of O's detectors separately everywhere, they're going to, it might be that observer P in their observer frame uses detectors that detect these two explosions to happen at exactly the same time. They are simultaneous. But P prime, or O prime, its detectors will definitely not detect the explosions to happen at the same time. In fact, the one on the right, the one with the larger positive x value, is going to happen first, followed by this one, because of their relative motion, that P prime heads towards the right in O.